I'm Stefano the Gironcoli. Paolo Giannozzi is there. If you saw this afternoon, we are going to talk a bit about different parallelization strategies that are implemented in PW, SEF, and many other codes in the quantum espresso distribution. And I have my slides that I will go through. Actually, Paolo had another series of slides. I couldn't merge them yesterday, and so maybe I will first go through mine, and then quickly maybe we can go through Paolo's one and see there will be repetitions, but maybe some more information. So let's do like that. Okay, so you have seen these days many things that can be done with quantum espresso and different codes, implementing DFT, implementing density functional perturbation theory, and other stuff, and they are all coded with the possibility of running on parallel machines, on multi-processor machines. And basically the two paradigms that are implemented are basically two. One is message passing interface, MPI, and the other is OpenMP. And basically they are different because MPI is a paradigm in which the different processor, different core run separate copy of the code, and they explicitly can communicate explicitly whenever in the code there is a communication call to an MPI routine, then this processor communicate, exchange data, collect results, or distribute some information to the other processors. And this is, however, the communication is explicit, so it only occurs when in the code it is one MPI routine is called. On the other hand, we have our laptops or the individual nodes of large computers are multiprocessor, and these multiprocessors share the same memory. And then actually there are other way of, let's say, have several cores to work together, and it is basically through the fact that they share the same memory. And so then basically whenever there is some task to be performed, different core can do part of this task and then feed or take the input from the same shared memory. And so then you don't really need to have explicit communication between different cores. And this is the OpenMP paradigm, basically. So this works with shared data on a multi-core, multi-processing unit. So while the message passing interface, MPI, is general, and its paradigm is that the memory has been distributed, so the data are scattered across different core, and you make explicit communication in which then the different unit may be different processor in a laptop or in a workstation, or different processors in a big supercomputer. Especially, this is, then you need, of course, a fast communication network between different processors. So this is something that is general, can go from a laptop to a supercomputer. Instead, the OpenMP require that the unit that the processing unit that use this paradigm have to share the same memory. So this can be, again, a laptop or a node in a big computer, but only the processors that are inside the node. And yeah, instead it cannot be, let's say, used to communicate between distant core of different nodes. Okay, so both of these things are implemented in Quantum Espresso. The MPI basically goes through explicit communication, so whenever you want, let's say, to broadcast some data from some root node to inside a given group, then you have to call a routine like that. If you want to collect the partial results of a sum and then have everybody have the total sum, then you call some routine like that. Or if you want to actually scatter some data from some, I mean, you have a distributed array and then you want to exchange this information of this array in which everybody send some buffer, send buffer and receive some other information from from the other, then there is some call like that. Or let's say one thing that is useful at a given point is to synchronize the different version of the code, the different version of the calculation, so that basically stop until everybody has reached a given point. This helps in keeping the overhead and the messages hanging around in the network, so preventing the network to be overloaded. So this is so then you can call a barrier. So this is what I meant by saying that the communication is explicit. You decide who has the data, when they want to broadcast or sum or collect, or so how these things is done, and this is hard coded in the code. On the other hand, in the OpenMP paradigm, you basically have your piece of code, and you have, for instance, a loop that where n may be very large, and so you can think it's a good idea to distribute this work and to do it dividing the, especially because there is no dependence. So what happens to the element I does not depend, j does not depend on what happens on the element with a j, different j. So every j is independent, and so this is a nice situation in which you can say the first core will do the first half of them, the second core will do the second half of them, the result is going to be put in the common memory, and so then everything is fine. And so this is something that you can do this kind of parallelization, so distribution of the work using OpenMP by using some pre-processing directive. So basically, these are comment in Fortran, and so anything that starts with exclamation mark is a comment, but if the comment has this particular, let's say, form, then the pre-processing, if OpenMP is implemented, recognize this as a directive for OpenMP, and so recognize that this piece of the code could be actually, OpenMP could be used to distribute the work inside the node. Okay, so, and it might be more, I mean, more complicated stuff, but basically this is the idea. Advantages and disadvantages. MPI is, as I said already 10 times, distributed memory, which means that you can actually use your computer the computer you have access to do big calculation, because if you distribute the data, then each individual unit only needs to contain a fraction of the data. So this makes this is good. On the other hand, the data distribution is something that you have to decide at the beginning, and so then it's kind of a big constraint on the code as it is implemented, how it is realized. And it is difficult to change. I mean, if you have decided that a given data distribution it was good, then if after a while you think that a different data distribution would be better, then to change these things imply changing basically the code everywhere. So this is a big constraint, but is what allows you to do large calculations because you are basically distributed the data, and each unit only deal with a fraction of the total system. It is pervasive and rather rigid. I mean, you can't really change it every second day, and so one better think, or at least try to think what is a good strategy that may be valid in general. And so, of course, all the calculation, this is effective if most of the calculation that you are performing are using the data that you have locally, because each data you don't have, you have to ask for, and so then you have to have a communication, and communication cost. And so communication should be kept at minimum, and so then computation should be as much as possible done on local data. But the important point is that if you are able to do this and use this distribution efficiently, then the memory requirement for the local process is reduced, and so then you can do a big calculation on a big computer, because locally you only have a fraction of the data. On the other hand, the advantage of OpenMP is kind of the complementary things, in the sense that if instead the memory, you are inside a memory sharing multiprocessor unit, then well, the nice thing is that, so the bad thing is that you are not reducing the memory. I mean, you have a system, and this is the memory you have, and so you are not, by using many threads, as they are called, you are not reducing the memory that the node needs. But what is good is that since the memory is available to all units in the node, then actually whether one loop should be parallelized with this method or not, and which variables should be used in part by some node and in part by some other unit. This is something that can be decided on the spot. It's not some general distribution that has to go across all the code. It's something that you can decide locally. And so this makes that the implementation of the OpenMP parallelization may be incremental, so that you have some, if you find that one particular spot is particularly time-consuming, then you can try to concentrate and use OpenMP to exploit OpenMP there, and this has basically locally, you can improve there, and this does not give you any constraint on how the data should be distributed in other part of the code. Okay, so I will talk mostly about message passage interface, because this is the one that really characterize the way data are distributed inside PW and the other codes, because this is, as I said, something that you can do locally. And so this is the main things that one needs to understand in order to try to use as efficiently as possible the resources that one is given. Okay, method-person interface then may parallelize, I mean, may be used to use parallel machines, and when you have so then you need a fast network. Yes?
What about between both? Is it more that one of the CPU like loops, let's say if I parallelize NPI in another loop, and then I could also parallelize with
Right. Yes. So the two things are can coexist. Yes, they can coexist.
But what would be more efficient? To have one of the CPU at the NPI level, or to have 50 CPUs at the NPI, and then let's say 2 at the OpenMP? Which one would be? Let's say there's no memory consideration, and it's gathering at the end is very fast. What would be the fastest?
It depends.
I think it depends. I think that inside the node, OpenMP maybe is good. Outside node, absolutely not. So there is a, let's say, so far I think in QE, in PW, SCF, etc., OpenMP is limited to a small fraction of the available nodes, in the sense that you may have, I don't know. Right, so you can use, I don't know, 4 thread, and then have two MPI processors, something like that. I think that one limit is that your calculation needs to fit the machine. So the less MPI processor you have, the larger is the memory. So then if you so this is the point. So you have to have enough MPI processor that the system fit, and then once you have that, you can play a bit with OpenMP and see if it is. But I would say in this moment, I don't know, Paolo, you may correct me if I'm wrong. OpenMP is working, but one should not push it too much. I think if you have many processors, I think you can do half of it. I mean, use 2, 3, 4 threads, something like that, but not pushing at the stream.
Well, I think up to 4 is up to 4 threads, 5, maybe 8, things like that.
Yeah, so this will probably change when you have many multiprocessors. But let's say if you have a reasonable, I mean, if you have 8 processor per node, let's say 4 thread is fine. Yeah. I think it's 4 should be a little bit faster, but I mean, there is a minimum basically, so then it should not matter too much. I mean, so I think that 2 or 4 should be more or less the same. I mean, 2 is better than 1, and 2 and 4 are, maybe 4 is a little bit better, 2 is a little bit. So there is, of course, a kind of minimum. So I mean, of course you want to optimize, but in the end, if you are close to the minimum, doesn't matter too much by the definition of minimum. No, so. But yes, so then, and of course, this is system dependent, and so then you never know. I mean, you can make all the benchmark that you want on some system, but then the system you are really interested in is never the one that you have done benchmark on. And so, but let's say reasonable choices can be taken. Let's say can be made, and then yeah, if you have much resources, you can try to explore and optimize, but let's say, right. So this is for, we were discussing what happens if you, whether use MPI or OpenMP inside a node, and so this is with some experience, with some tests you see. But the other thing is when you have to communicate between different nodes, and then you have the network, and the network is is, of course, very important, and two things are important, basically the bandwidth and the latency, in the sense that whenever you communicate, there is the time, so communication cost, time, and this time is proportional to how many data you exchange, and so this is going to be determined by the bandwidth, so how fast the data transfer is. But the other thing that is important is the latency, in the sense that this is how much time you spent in establishing the communication. I mean, the first time that you want, when you want to exchange some data, then you have basically to establish a communication channel, and this costs some time, even if you then want to exchange 1 byte. And so these two things are important, and so one has to try to communicate possibly few times large amount of data rather than many times just a few bytes. But this is not always possible. So anyway, these are the two things that one should look, and then let's say better computers, a more efficient computer from the parallel computing point of view are computers in which the bandwidth and the latency are, bandwidth is large and latency is small. Yeah, disk I/O is bad, so actually you should avoid, one should avoid as much as possible disk I/O, and even more so on parallel machine, because actually I/O on parallel machine is rarely done in parallel, so there are actually only a few nodes that do I/O, and so then, which is already bad in general, and if then only few nodes do it, it's really a bottleneck. So this is why when you have many processors, then you also have access to, your RAM, your memory is large, and so one choice that now is taken most of the time in Quantum Espresso is that you try to keep everything in memory. So even if you have many K points or many copies of the quantities, you keep all these things in memory, and you don't write the result to the disk up to the end. Okay. And this is it, what one wants in principle. You want to minimize the time you wait, and if you are doing a calculation in parallel, then there is your perfect code has, well, not your code, not the perfect code. Your code has a fraction which is scalar, a fraction which is parallel, and then you have some overhead coming from communication. And what kills you in the end, if you, of course, the fraction of the calculation which is parallel, as if it is perfectly parallel, as you increase the number of processors, goes down, and like 1 over n, and so this eventually will not count much. It will count less and less if you have more processors. Eventually, the communication overhead will increase, but what really happens is that sooner than the communication overhead sets in, the scalar part is the dominant, the one that is left, basically. So every part of the code that is not parallelized is going to be repeated on each processor, and this is the part that will dominate the time that you wait. Okay. Another thing about scaling, when we talk about, we have our code and we put we do a calculation, actually and we ask how well the code scales. Well, there are two things that go under the name of strong scaling and weak scaling. Meaning, what happens if I have one calculation in mind, one system size in mind, and I want to increase the number of processors and see how fast it can go. this is strong scaling. So your system size is fixed, and you try to use all the machine to do that. On the other hand, the other thing that happens is that since you have access to a bigger machine, you want to do a bigger system. So then how things scale when increasing the number of processors, we also, let's say, increase the size of the system. These two things are not the same. Strong scaling is much more difficult to achieve. And unfortunately, sometimes, I mean, in computer centers, there is some constraint sometimes that you need really to use, I don't know, 1,000 processor, 1,024 processor, even if you want to do bulk silicon. And so then, if what you want to do is bulk silicon, then you have the problem that you have to basically achieve strong scaling, because you don't want, it would be nice not to vast a lot of resources just because we are forced to use many processors. On the other hand, many times we don't really need to do one huge calculation, but maybe we need to do many small or medium size calculations. So the other options would be actually to use a fraction of the machine to run each of these medium or small calculations, and then make many calculations in parallel. So this is another way of parallelizing, and depending on whether you are interested in one single system or many systems, this may be another choice. So I mean, this is using more processor always have some overhead coming from communication. So in principle, if you can use the same processor to do several independent calculations separately, it's usually a better idea if you can organize the workflow in such a way. Okay. Okay, so let's go back to method passage interface. So basically, what happens is that if MPI library is a variable, the code starts with something like that. Let's say you start this, I mean, you invoke this library, and basically the code starts several copy. I mean, the system starts several copy of the code. And for instance, for PW, this is how you call it in the example that you have already done these days. So this is what you basically have. So you have something like MPI run, and then some number of processor equal to, for instance, 4, the number, the code, and then input output. And so basically, what happens is that 4 copies of the code are running. Each core or each unit execute the code starting from the beginning and follow the structure, and only acting on the data that has a variable. And then, okay, so each code maybe is one of a group, and so it's important to know, I mean, it's useful to know what is its number and what is the size of the group in which it belongs, and what is its place in this group. And okay, in MPI there is one communicator that is common word, which is the global, is the default communicator that contains all the MPI processors. But you can have, and we come to that in the following, you can define derived communicators, and so you can subdivide the parent group, a parent group that is identified by a parent communicator, into subgroups, and with something like called MPI common split, in which you say basically you define, for instance, intra-group communicator means that all those that have, divide in two groups, group 0 and group 1, and inside the group they are numbered 0, 1, 2, 3, 4, 1, 2, 3. Or you can do the opposite, have 4 groups of 2, so 4 groups which are 0, 1, 2, 3 in the intergroup communicator, and inside each of these intergroup communicator, they are numbered 0 and 1, 0 and 1. So, okay, so you can split things like that, and basically you can then subdivide the work in subgroups, and then you can collect information or distribute calculations inside the one subgroup, and then collect the result across the subgroup using the intergroup communicators. So basically, this is and by doing this and repeatedly, you can have a hierarchy of parallelization levels. Okay, this is things that we already basically touched. So different typical basic communication operation that we can do. Let's say, what is to make things more practical, what is the typical things that we need in density function calculation in plane waves? So basically you have a number of wave functions that are identified by a number of, some vectors with a band index and a set of plane waves. And maybe you want to do the scalar product with some projector, some other vector beta with another index over projectors, and with, of course, the same plane waves. And then this is what you want. So this is typically in PW and in the other codes of quantum espresso. These are the big objects. I mean, we run calculation for a system that has many wave functions, many wave functions on a basis set which may be large if the system is large. So this is it. So we have basically what we want to do is to make this product. And how do we distribute this data? So there are many choices possible, but the choice that is done in quantum espresso is basically that the plane waves are distributed. So the plane waves, the basis set is huge, and so if you have any system which is not bulk silicon, this number of plane waves may be thousands or several tens of thousands, and so this is a number that you can distribute across processors, and comparatively the number of electrons and the number of projectors and all the other quantities is less. And so we thought, it was thought to be a good idea that the plane waves will be distributed, and each processor, let's say, which is identified by different colors, will own data for all the projectors or all the bands, but only a fraction of them, only a certain subset of the plane waves. And then when we have to do this product. What we want in the end is the product of the transpose of the beta matrix times the wave function matrix. And so what we need, and this is something that everybody will need, every processor will need to go on in the calculation, will need the product of these two vectors. So how it is done? Well, first, everyone does the product on the local data. So the first processor will make the product of this part of the matrix, the transpose of this part of the matrix times this part of the matrix, and will generate a blue matrix with this dimension, okay, by calling, for instance, a LAPAC routine that does exactly this. So the Z-gem of this data, and these are all local data, so this is what everybody can do without knowing what the other have done. So at the end of this operation, each processor has a partial sum, the sum over the process over the plane wave that it own, and this is it. And then you collect, so you make a sum across the processors of these partial sums, and when you have done this, then you have obtained the sum over all the plane waves. Okay. So at the end, so once you have called this MPI sum, then this is it. So beta psi is a array which is present in each processor, that after this operation is different in different processor because it corresponds to the partial sum. But once you have called MPI sum, it's going to contain the sum of across all the processors. And then this is the quantity that you want to use to progress your calculation. So this is one example, but you can imagine that every time we do operation, so we do operation locally, and then we try to do to collect the result as with some MPI sum thing. And of course, we could have done one. I mean, this could be a double loop over I and j, and we could have done this scalar product on every single pairs of projector and wave function, and then we could have made the sum for each individual element. But this, of course, is not convenient for two reasons. Why? One is that gem is one of the most efficient routine in LAPAC, and so if you or BLAST, whatever it is, and so if you actually want to do matrix multiplication, is one of the most efficient things that you can do, rather than making many dot products. And the other thing is that in this way you communicate once. You communicate once instead of communicating several times, and so you pay the latency only once, and okay, the bandwidth is what it is. I mean, the number of data that you want to exchange is given, and so this is it. But in this way, you pay only once the latency. Okay, this is fine whenever you do operation in the reciprocal space, so dot products or things like that. The problem is that many things, for instance, the density is defined in real space, and so a distribution of data of plane waves, a plane wave does not correspond to any location in space. So actually, you have to have a different distribution of data when you are in reciprocal space or when you are in real space. So this is the other piece of thing that one needs to keep in mind when thinking how the code works, how the data are distributed in real and reciprocal space. So in reciprocal space, we said, for instance, our wave function, EVC, is the typical name of a variable contained in the wave function. The eigenvector, complex eigenvector, typically, are distributed like that. However, we need sometimes we need this object transformed in real space. So we need to fast Fourier transform this data. Okay. so we need two things. So we need a grid, a fast Fourier grid, and we need to define how this fast Fourier data in this fast Fourier grid are distributed in reciprocal space or in real space. So the choice that is made is that in real space, different processors own slices of the space. So if we have 4 processors, one processor will own, let's say, the top fourth of the z direction is the vertical one. So the first processor will own the bottom top. The second processor will the bottom fourth. The second processor will own the second fourth of the slices, and so on and so forth. Okay. When instead we are in reciprocal space, the quantity that is distributed, so the quantity that each processor owns, are basically columns in the FFT grid, because only the plane waves that, let's say, are contained inside a sphere that is defined by the cutoff are actually non-zero, have non-zero component. And so only, so not all the space is filled, so we don't need actually to distribute columns or plane waves that are outside the sphere, that would not be intersected by the sphere, but we need to distribute a certain number of columns. Okay, and so we can actually distribute the different processor will own different column along Z, a subset of full column along Z. And if you collect this column, they will basically define a set of G vectors, and a different K point will actually need different subset of these G vectors, and so there will be an index, EGK, that will bring you from this vector containing the G vectors to the index that we were using before to say, okay, these are the plane waves that define this wave function. Okay, so there are 1, 2, 3 things. So there are the indexing of the plane waves, the indexing of the G vector that corresponds to that plane wave, and the place in this FFT grid that correspond to a certain position in this G vector list. So there are indices that goes from one to the other and allows you to bring your wave function to copy, let's say, your wave function into a location in this grid, so that after Fourier transform you have the wave function converted to real space. Okay, so there is this indexing, but eventually, after, let's say, copying the wave function on the FFT grid in reciprocal space, which means having put this Fourier component inside these columns, then you need to Fourier transform. And the Fourier transform is a three-dimensional Fourier transform, and so is basically the subsequent application of 3 FFT. So one FFT along Z, one FFT along Y, one FFT along X. The first one along Z you can do locally, because each column is, each processor contains full columns. So along Z you have all the information to do the FFT. So you can do one-dimensional Fourier transform along Z, and then you basically transform your function from something which is totally defined in reciprocal space, to something which is in part defined in reciprocal space and in part is in real space. Along Z, now things are in real space. But this is not what you can use to do the second two Fourier transform, the one along x and y, because now the data along x and y are scattered around different processor, and so this is where actually the communication enter. So there is one routine that basically scatter the data across processors, the one that are belong to the group for which this RNG parallelization is performed, that basically redistribute the data. So the data are the same, but now they are organized in this way, so that all the G vector x and y, all the different gx and y for some Rz are collected together. So you pass from having all the column of some gx, gy to have a partial column of all gx, gy. This is the time-consuming, from the point of view of communication step, the time-consuming step from that point of view. And then once you have done this, then you can do a two-dimensional FFT in x and y, and then you get your results in real space. Each processor then has only a fraction of the total wave function, the one that corresponds to this set of planes. And if you want to go back, you do the opposite. So you do first the FFT, two-dimensional FFT in real space, x and y. Then you scatter again, with the inverse routine of the previous one. And then you Fourier transform back in reciprocal space. And then you copy, using these indexes, you copy back to the original array. OK, so this is, in a nutshell, what RNG distribution is and how most of the communication time in the code goes. OK, so there are several then. So this is one basic. Sorry, let's see. Yeah. OK, so these are the main distribution, the main idea of data distribution in PW, in quantum espresso in general. But there are, as I said, there are several levels of parallelizations that can be used. So the basic one is the one that I have described. So if all the other variables that, all these other communicators, all these other additional type of parallelization is set to 1 or are left unspecified, which is the same, then this is what will happen. All the processors will be distributed, will actually participate in this RNG distribution. And however, this may not be super efficient, because one obvious limitation is that you can't distribute more planes than you have. So if your calculation has a certain number of plane along the z direction, I don't know, 128. Then if you want to use more than 128 processor, there will be some processor that has nothing to do. And so this is not, and then, you wait, there will be 128 that do something, and the other that will wait it idle for those other 128 to finish. So you may have, there might be other things that you can do. One thing that you can do is, if your calculation has many k points, basically many operations are not independent. Each k point, the k point are weakly coupled, basically, because most of the time is spent in solving the Kohn-Sham equation for a given potential. This potential, of course, depends on the density. The density depends on all the k point, but
most of the time the potential is given and you want to find the eigenvalues. And so for a given potential, each k point is independent. So if you have many k points, you can think that the part of the calculation in which you basically diagonalize one after the other the Hamiltonian for different k points could be split. You could then introduce a number of, divide your group of processor in pools that using nk or n pool or n pools. So they are all alternatives that are reduced to the same. So you distribute your processors, you divide your processor in subgroups. And then inside the subgroup, you do the RNG distribution I was talking before. So, for instance, if you have, 10 k points, you could, and you have 1024 processors, then you may want to do, divide 8 in 8 pool with 128 processor each, and then the 128 will deal with one single k point, so that you will do the RNG distribution as I mentioned before, and then each pool will deal with a subset of the k point. So if you have 10 k points and 8 pool, this is not ideal either, because then this means that there will be some pool that makes 2 k point and some pool that will do only 1 k point, and so there will be again many of the pool that will be idle, waiting for a few of them to finish the second k point. But let's say this is one way in which you can go to extend this. For sure is better than trying to use all the 1024 processor to run each k point one after the other. There are other things that can be done. For instance, there are calculations like nudged elastic band calculation, in which basically we are running. This is used for estimating transition barrier in chemical reactions. So you basically have a chain of similar systems with the same number of atoms, the same cell and everything, but different positions that describe a path from some initial to some final state, and basically you have to repeat these things and optimize the path. So each image is a separate calculation. So again, and the system needs to communicate, the different images interact very weakly. They only interact at the end of the cell consistency. So it's a good idea to parallelize across these images. If you have, if you do some NEB calculation, or similarly for the phonon code, when you calculate the dynamical matrices of a system, basically you are solving you are calculating the response of the system to many displacements that are organized in irreducible representations. Each irreducible representation has to, so the pattern corresponding to the a given irreducible representation has to be dealt together, so you cannot distribute them. But there are several irreducible representations, and these are independent. So you can again use image parallelizations to distribute the different irreducible representation, and this basically scale linearly, because each irreducible representation is independent. Okay, so this really is a way to distribute data that are not coupled, and so basically you can
scale very well in this way. But, okay, these are kind of specific things, whether you want to do some phonon calculation or you want to do some NAB calculation. There are additional, instead, type of parallelization that we can use to try to extend the scaling for a given system. And these are band parallelization, task group parallelization, and linear algebra parallelization. Let's see if there is, yes, so something like that. Okay, so these are the one that I already described, basically, no? So RNG is the fundamental one, and its advantage is that, well, its disadvantage is that it's high, needs a lot of communication, because it's something that you do every time you do an FFT, which is always, you need to communicate. However, the memory is really distributed, and if you have a good network, this is quite efficient. If you have many k-points, definitely k-point parallelization is something that you can use, and do not require much communication, because you basically need to collect the result over all k-points after the diagonalization and to build the charge density, and then things are basically again decoupled. After you have the new density, then things are again decoupled. So, however, each group of processor that in which you divide the system needs to be able to deal with a full k-point. So you are not really reducing the memory. So if your problem is that your calculation doesn't fit the memory, then you need to increase the number of processors, and you need to use more processor in the RNG parallelization. Once this size is reached, so that your calculation fit your system, your calculation fit in a certain number of processor, then if you have many k-point, it's a good idea to extend the scalability of the calculation by making many pools of this size. Each of them is able to deal with one individual k-point, and by replicating this, you can, depending on how many points you have, trying to have the same number of points in each pool, then you can extend the scalability of the calculation. If you are running with a NAB calculation or a phonon calculation, then this image parallelization is even viable and useful, because it requires very little communication. However, of course, you cannot use this to reduce the memory, because each group is doing a full calculation of the system. You are simply doing more copies of the system together. But so the first thing is take the smallest set of processors that fit, for which your system fit, and then try to extend this by k-point, and if you have the possibility, NAB, image parallelization for extending scalability. So these are the three basic things that I mentioned, but there are three more levels. Two of them kind of compete. So let's see. I mentioned that this basic strategy is that we distribute plane waves, and that every processor basically have some fraction of plane waves for all the bands and all the projectors. However, this is not necessarily, I mean, one could also think that also the bands could be distributed. And in Carparinello, for instance, this is done, can be done by using this band parallelization. So this is an additional level of parallelization in which inside the pool, okay, so inside the group that deal with one K point, you divide this group in a certain number of band groups, and then inside each band group you do the RNG distribution. Or if you want the other way around, I mean, you have a set of processors that is needed to describe RNG, then you can duplicate or, I mean, replicate a number of times depending on the band parallelization, and this bigger group is what we call pool. And if we have many bands, then again, we can, many operation, in Carparinello, basically what you evolve is the wave function in which the Hamiltonian is applied repeatedly to all the wave functions, and so basically it's a good idea it may be a good idea to divide this wave function in blocks, and each subgroup, each band group will deal with some subset of bands. Okay, this is one thing. On the other hand, instead, independently from that, as I already said, in the FFT description, we are kind of limited by the fact that we cannot do this Fourier transform. I mean, it's not efficient to do the Fourier transform with more processors than planes, because if, I mean, it would not be efficient to have some processors that do not have plane. However, in the search for extreme parallelization, it may happen that you really want to use many processors, more processors than planes. So what is the solution, or what is one option, is that to do many FFT together. So you have many wave functions. So I mean, if you want to do 10 wave functions together or 4 wave functions together, so if you know that you need to do 4 FFT, then you can actually pack and redistribute the data in such a way that you do 4 FFT together, and each FFT will deal with only one. A subgroup of the processor will deal with one wave function, another subgroup will deal with the second wave function, another subgroup will deal with the third and fourth wave function, and so then this means that again you can extend the scalability of the code. If you're able to do this efficiently, you are doing this. You can extend the scalability of the code. So this is the task group. So task group is something that, especially in Carparinello, where again you do all the calculations are done on all the wave functions together, and so you know for sure that you have to deal with many bands, So whenever you need an FFT, you know that you need many of them, and so you can basically use this. But you see that these two things a bit interfere, because we are basically talking about the same wave function. Either you want to split them as band in the band parallelization or in the task parallelization, they are basically the same data. So these two things a bit interfere, but they are both present, and in the PW, the task group is mostly used, while the band parallelization is actually used in some part of the calculation only in the additional, very heavy part that deal with hybrid functional, so with exot exchange, FOC exchange, which is a very demanding part of the code. And so there, band parallelization is used in PW. Instead, it is used in many places in CP. And task group is, anyway, introduced for both, and can, again, extend, therefore, the scalability to a number of processors which is larger than the number of planes that you may have in the third direction. Somehow independently, another thing that the PW and Carparinello do is to diagonalize matrices, fully diagonalize. I mean, what they do, PW perform iterative diagonalization with the Davidson algorithm, for instance, in which you never actually calculate the big matrix, but you calculate some reduced estimate of the Hamiltonian on some trial-wave function, and then you diagonalize this reduced matrix, which are small. Small means 2-4 times the number of electrons the number of bands that you have, which still can be large. I mean, can be a few thousands, and you need the full diagonalization of these small matrices. And in the Carparinello, instead, you need to do the orthogonalization step, and the orthogonalization step, I think, involve similarly the diagonalization of some small matrix of the dimension number of bands times number of bands. So there is another parallelization level which is independent from all the others that basically call Scalapack or some other homemade parallel diagonalization that allows to perform this diagonalization of these small matrices, but if they are not parallelized, then this is going to be that scalar part that actually kills you in the end. So this is about the different type of parallelism that are implemented. So let's see what I was discussing. Yeah, okay, so this is the coming back to the discussion about OpenMP and MPI. So you can only use OpenMP inside the memory sharing multiprocessor, and then one has to kind of see and test a bit whether it is more convenient how much is convenient to push on the OpenMP end or MPI end. I mean, this is something that it is convenient, but I think it's not convenient to put at the extreme, and it's not probably convenient to just do all MPI processors. So it's something in between, and depends on the system as well. Whenever you can, use K-point or image if your calculation allows you, because they involve low communication and of course the smallest unit. I mean the the set, the number of processes that you use for the basic parallelization has to be large enough that the calculation fit, of course. But then, if you have k points or images, then this is something that you can use to extend the scalability. Beware of the fact that there is some granularity, in the sense that if you have 10 k points, maybe it's not a good idea to use 8 processors, 8 groups, because then you have to distribute 10 k points across 8 groups. And so you will have 2 groups that try to do 2 k points and 6 groups that will do 1, and then you have to wait. And instead, maybe it's in the end more convenient to do, I don't know, just four groups, because then you have 3, 3, and 2, 2. So which is better than 2, 2, 1, 1, 1. So I mean, it's just have or if you have a small number of images, you should kind of choose the number of images in such a way that each subgroup deal with the same number of replicas of the system. And right, so this is it. And so, because in principle there is very low communication, but if you distribute the work in a balanced way, then it is convenient. If you distribute them, if you make a bad choice about the number of pools or the number of images, then you're actually communicating very little, but you have some processor that will stay idle for a lot of time. RNG space distribution is actually what you should be aim at. I mean, this is the fundamental things, because this really distribute the memory. So if you want to do a big system, this is what you have to do. You have to take a number of processors large enough that you can fit the system, and it is efficient. It is communication intensive, so you should not try to push it too much. Also because in the end you are going to be limited by the number of the planes that you can basically distribute. So if you have a huge number of processors, but your system is small, you cannot hope to be very efficient in the FFT parallelization, just pushing the number of processor to the extreme. But in that case, you can work on the scalability, to extend the scalability using the task group. So when you can basically collect different FFT, different wave functions to do FFT together, so to extend this limit. Or similarly, you can, in a kind of similar and competing way, use band group parallelization. And if the diagonalization of the so-called small matrices is going to be at the end what the bottleneck, then one has to deal with the parallel diagonalization of those matrices, and then the diagonalization is to be used. Okay, so this is the end of my slides. Okay, so I'm about half, a little bit more than half of the time I was allowed. Let's see Paolo version of the same thing. So hopefully we can do faster. Okay, so this is slides Paolo had. So this is what, I don't know. different types of calculation.
Is that way just
Right. So you see, orthogonalization is the diagonalization, and so you see that the diagonalization keep, okay, here doesn't scale so much, so well. Instead, the H psi, which is this is Carparinello, right? No?
this is Carparinello, but this is an old picture, and instead just to make some color because.
Okay, but let's say you see H psi, which is basically the force, the generalized force in Carparinello, is something that scales very well. But in the end, you have to orthogonalize the wave function. You need to diagonalize the small matrices, and the small matrices do not scale. Okay, I don't know which version of diagonalization was here, but you see that this is actually not totally scalar, but it's not really scaling very, very well. The density, rho of R, takes less and scales also rather well. And then what is update? What is update? I don't know. Anyway, doesn't seem to scale very much. So it's true that H psi is the most important part, but eventually, actually what you pay is other things that that remain scalar. So even if you have a huge system and you have a huge number of processors, then in the end, the part that you didn't parallelize sufficiently is what kills you. Okay, MPI, OpenMP, Quantum Espresso exploit everything. Okay, there is a completely separate version, mostly implemented by Filippo Spiga, that ported part of the code, Quantum Espresso code, to GPUs, and there is a website, etc. But okay, we are not talking about that here. MPI basically is viable in all architectures if MPI libraries are installed. Can be very efficient. Actually, the RNG distribution that I was mentioning is efficient until it reaches its limit. And if MPI libraries are well installed, and the communication hardware is good, then it is. This is what you can obtain. And so for this, you can scale to a large number of processors. But if you decide to change something in the organization of the code, then you have to rewrite the code, basically. OpenMP is, in principle, something that you can do locally, as I mentioned, and so you can do it incrementally and without rewriting too much. But it is limited inside the multi-core CPU and can be used in combination with OpenMPI, and again, one has to see how to blend the two schemes. Okay. And anyway, so far that the multi-core processor meant for 8 processors, it was limited, but now the new processor will be, I don't know, 64 or something, many individual core, and so then this may be something that 68 for some reason, not 67, that would be even better, but yeah, 68, I don't know, yeah. Well, okay, but 64 and then 4 for I/O, maybe. Yeah, I know, but then we should use 4 for, I don't know, just memory or some I/O, and then 64 for whatever. Anyway, okay. Yeah, this is something that I didn't put, actually, but these are basically the main variables, I mean, the dimensions of your system. So how many, so this is the huge number, how many plane waves you have. Even more, actually, this is the number of plane waves for the wave function expansion. Even more is the number of G vectors, which is 8 to 20 times larger. The FFT dimensions, these are all depends on the volume of your system in a certain sense, and on the cutoff that you use. And then, of course, you have a certain number of atoms, a certain number of electrons, and a certain number of projectors, which they are close. I mean, they grow in the same way. I mean, they are not exactly the same, but basically the number of the number of electrons, the number of bands, the number of projectors, they are more or less of the same order. And of course, if you have many K points, what is important is also the number of K points. So typical things, the number of plane waves grows with the volume, which, however, also grows with the 3/2 of the cutoff. And the number of G vectors is proportional to the number of points in the FFT grid, and it is a factor of 8 to 20 with respect to the number of plane waves that you need for describe your wave functions. And this 8 is the minimum that you have basically when the cutoff is 4 times the cutoff for the density is 4 times the cutoff for the wave function. And 20 is what you have for ultra soft, in which the cutoff for the density has to be taken larger. Projectors and electrons are, let's say, 10 times, you have, let's say, about 10, or, I mean, from a few to about 10 electrons per atom. And similarly for the projectors, and anyway, the number of atoms is much smaller than the number of plane waves. So the big number here is number of plane waves, and this is why this is what we distribute in the code. Okay, things that you need to do is calculate the density. So you need FFT, a lot of linear algebra, matrix multiplication to do the beta psi that I mentioned at the beginning. And once you have the density, you build the wave function, the potential. This basically need operation on the grid. So you need again FFT and operation in real space. And then you need to diagonalize, so we need to apply H psi many times, either to diagonalize in PWSCF or to evolve the Carparinello wave functions. So you need H psi, and this again is FFT, linear algebra, and so on and so forth. So you see, basically we do FFTs and linear algebra. This is what we do. And then we need to do subspace diagonalization or orthonormalization of the Kohn-Sham orbitals. And so this is again diagonalization of small matrices, where small means a few thousand by a few thousands in big systems, and additional matrix multiplication. So this is where we need. So basically, most of the time goes into linear algebras, which are efficiently implemented by calling libraries like PLUS, LAPAC, and in FFTs. And so the local operations are done using libraries that are hopefully efficient, and then we need to communicate. So most of the memory is spent keeping the wave function. If we have many K points and we choose to keep everything in memory, then we have many copies of the wave functions. And this is, of course, increase the RAM, but allows not to use the disk. And so this is actually very convenient now. I mean, if you have access to a big machine and that you can afford keeping everything in memory, definitely this is what you should do, because writing to the disk is very inefficient. Once you have dealt with the wave function, you need a new density, and there will be a few copy of density, potential, and things that use for the mixing strategy, etc. So these are a few, let's say, 10 copies of these objects. In order to compute the Hamiltonian, we need to describe the pseudopotentials. One important thing in the pseudopotential is the projector, the projector in the Kleinman-Bielander arrays, projectors. So this again is something that involve many vectors basically, but this is of the order of so it's like another wave function set. So it's like another. So number of projectors is of the same order as the number of electrons. So this is again something that costs, but it's of the same order as 1 K point. And it is over, I mean, it's regenerated. You don't need to keep in memory. This is fixed, and so something that you can actually recalculate fast in a fast way whenever you need it. So you don't need to keep several copies of them, one for each K point. So you need to only remember how to build them when you need it. Okay, and then there are these other matrices that, okay, so this is more or less what you said. Yeah, okay, what we want to reach, what we want to obtain is balance. So we need to distribute work and data as much as possible in a balanced way. And do not communicate as much, communicate the least possible, because this is what actually where we have an overhead. I mean, if in the serial case, we don't have communication. So by distributing the work, we are reducing the time, but the need of communication adds something that we need to keep to the minimum. One thing that is important if you want to do big system is that all the memory is as much distributed as possible, so that all the wave function and density, etc., needs to be distributed. In particular, everything that depends on the number of atoms on the unit cell, etc. So everything that grows with the size of the system should be actually distributed, because otherwise this is what is going to for big system, this is going, if you don't distribute it, then it's going to be the one that blocks you, I mean, that give you, okay. Communication, MPI is dealt with through communicators. You can, for instance, distribute, as I mentioned, if you have an adjusted elastic band calculation or a phonon calculation, you can basically distribute the replicas of the calculation that you want across different images, I mean, subgroup. So here we are taking the opposite. We start from the big, and then we are going into the inner thing. So that whenever it is possible, if you have many copy of the calculation that has to be done together, like in a NAB calculation or like in a phonon calculation, or there is another code which is called many PW, in which you basically have many copy of the same very similar SCF calculation that you want to run. with a slightly different input, then you can invoke this many PW code that can use this image parallelization to basically split the work across a subgroup of processors, and basically you say I have 64 processors and I want to run this NAB calculation, but I divide this 64 in 4 groups, each therefore of 16 processor, and each group of 16 processor will deal with an image, will deal with a subset of the NAB calculation that will deal with a subset of the copy of the calculation in the path that connect the initial to the final state. This has the potential to be really linear scaling because there is very little communication between different images. The number of images should be chosen wisely because if, so that each image deal with the same number of replicas of the system. Right. And the image, of course, the memory does not scale in the sense that the calculation needs to fit the 16 processors, and then you have 4 copies of this calculation, slightly different input, but the same system basically. So you need your fundamental system needs to fit the 16 processor that you want to use for the single image. So you are not scaling you are not distributing the memory in that sense. But when usable, it is a good option, especially if the communication hardware is not so fast, because you communicate very little, and so then the fact that it is not so fast is not really a problem. Okay, this is some specification of what are the routines that are used for that. But let's say below the image parallelization, there is the key point parallelization. So if you have several key points, then you can actually distribute. So this our 16 processor that we identified before, let's say, let's forget about the NAB calculation. Let's say that we want to run a calculation that requires 16 processors. However, not that requires 16 processors, but we want to use 16 processors, but our calculation would actually fit in 4. Okay? So then you can, and we have more than 1 key point. We have more than 4 key points, let's say. Then it may be a good idea to say, okay, we use 4 pool, or nk equal 4. So that we divide these 16 processors in 4 groups, each of 4 processors, and then the R and G distribution is performed inside these 4 processors, and the result of the partial summation over k points is then performed and collected, and the density is collected, and then the new potential is built and then redistributed, and again you different pool deal with different subset of key points. Okay, again, number of pool. This is not true, in the sense that it's not true that number of pool must be a divisor of nk. If it is an exact divisor of nk, it's the optimal choice, in the sense that you don't have remainder. If it is not the whole divisor of nk, then you have a remainder, and so there will be some pool that make one extra key point with respect to the other, and so this is the smaller is this, the bigger is this imbalance, the worse it is. So I mean, one should try to take this n pool number such that the distribution of k point is as balanced as possible. Okay, so the optimal choice, of course, is that n pool is exactly a divisor of nk. And again, since most of the calculation is done, for most of the time, the k points are basically independent, then there is very little communication involved. The only communication needed is at the end when you collect the results, you build the new density, then you need to basically make the summation over the partial set of k points that you have, and then collect the full result across the different pools. And so this is very, again, convenient, but again, the memory doesn't scale in the sense that the calculation, one single k point, which is basically the full calculation, needs to fit in the small group of 4 processors. So if your system fit in 4 processors and you have many k points, then using the pool parallelization strategy is a good idea to extend the scalability to larger number of processors, basically. Yes?
As soon as one pool is done with a k point,
right.
it gets immediately another from a list, or those are assigned?
Those are assigned at the beginning. So you have 10 processor, and then you know he is going to do the first 3, and then the second pool is going to do the second 3.
Basically, that contradicts the previous statement about determining an ideal number of k points per processor per pool, because it says also that some k points might require longer time than others.
Yeah. So yes. But so what you suggest, what you say, one could do that one start and as it's finished, get another k point, right? But then getting another k point means to getting it from somewhere. So you should communicate and transfer this information.
But
so this
done at the beginning anyway. I mean, at the beginning you have to transmit those k points.
At the beginning you generate the wave function, and so each generate the wave function independently. So you don't need, I mean, you know how to generate your wave function. But if you were to do, I mean, if I'm idle and I would like to do the k point of someone else, but I need to get their wave function to start from, where to start from in the iterative diagonalization. So this is not done, yes. So this is why, and the same thing is for the image in principle. Also the images, not all images may take the same number of iterations to converge. So I think ideally one would, I mean, if everything was perfect, you would say, okay, I take as many images as my replicas, every one makes just one, and it's fine. And the same thing for the k point. I have as many pool as k point, and each does only one. It's yes and no, in the sense that if you have only one, then the full calculation advance with the slowest k point that you have. I mean, when you have a chain work, you go with the pace of the smallest one, because of the slowest one, because everybody has to wait for the slowest to finish. So this is why I would say it's good. Beware about granularity was said somewhere. So I mean, it's maybe good to have 2, 3 k points. I mean, if you have many k points and you have 2, 3 k points, then this more or less balance. I mean, statistically they will balance. Instead, if you insist on having just 1 k point per pool, this is something that then you wait for the slowest one to finish. So it's a trade. I mean, it's a trade-off.
But even with a very good communication, it wouldn't make sense to assign them dynamically?
No. I don't know. It's a bit.
Complicated.
Yeah, it's complicated. Yeah, this is the point. I mean, MPI, if you want to change something in the MPI strategy, you need to rethink the code. I mean, it's, yeah, I think.
I think actually, large elastic band, there is something like that.
Yeah, because in the large elastic.
These are dynamically allocated, but well, first of all, the code is a mess. The second, each image has to read the data from the previous step. So,
I think.
no figure because it takes a significant amount of results.
We could have the four nodes of the 68 node keeping in memory and ready to distribute data from. I mean, yeah, I don't know. It's.
But at least that time depends on symmetry considerations, right? I mean, the difference in time for calculating within a k point
Yes.
depends on the symmetries that are available.
Well, the number of k points that you have depends on the symmetry. The higher, the higher the symmetry, the lower the number of k points. But I think inside a given k, I mean, for a given set of k points, which k point is more difficult to converge, I think may also depend on whether it is high symmetry or low symmetry. But not that much, I would say. So I mean, yeah, okay. So in principle, there are many options that one could play with, but yeah.
Assignments in the beginning, like put in all high
Right.
symmetry and all low symmetry.
Right. This is done sequentially now. Yeah, this is something that one could, if one has a good estimate of which one would be more difficult to do and which one would be, then one can try to use this heuristic to distribute them in a more balanced way. But okay, we don't have such a heuristic. But in principle, yes, if one has some heuristic for that, one can try to incorporate this. So without, so that would be, let's say, easy to change because this is just which k point you distribute. It's just a reorganization of a small set of data. Copying the data from one to the other is also something that one could do. I don't know. Yeah, I think it's not very big. I don't think it's a very big difference. And it's probably system dependent, so you don't really know before doing the calculation, and once you have done, you don't care. I mean, yeah, the other thing is, I would say, when this is useful, when you have many k points. I mean, if you have a big system, you end up having very few k points. So then you have, I don't know, four k points, and then you have 4 bands, and then pools, and that's it. I mean, you do one each, and you can't do better than that. Or you have a metallic system, so which has many k points, and then the number of k points that each pool has is large, is 10 or 15. And then, on average, they doesn't matter so much. But you're right that this is something that one could think of, but one has to find out how convenient it is, whether it is convenient or not. And then, if it is convenient, then one has to think how to rewrite, because then it would be some significant rewriting. So, yeah, in principle, it's an option, but it's not implemented, and I don't know if it will be considered anytime soon. But yeah, in principle, it's true that one could do differently. Okay, so that's it.
I also have a question. So, considering the architecture of the user cluster machine, should we limit the number of processors processor per pool to the number of processors in a node. Like for example, if we have 16 processors in a node, should we make it so that we don't have more than 16 processors per pool to communication?
If the communication outside the node is much slower than inside, this could be a good strategy, because then because the communication involved in this part is very small, and instead the communication for the FFT is so limiting the FFT inside the node may be a good strategy. But if you have a very good communication, then and you want to do a big system, you simply can't really have your system inside a single node, and then you are done. Basically, you have to use it.
And the thing is, if we wanted to do this, does the code prioritize taking code from the same
I think, but I don't know. This depends on the scheduler. I mean, how things. But I think that. I'm not sure, but
Yeah, normally processor.
right, I think so. So I mean, the first node, I mean, they are given sequentially, and the first block is in the first node, the second block in the second node, etc. So, and this is the way they are distributed. So the inner parallelization, which is the FFT parallelization, is are the contiguous nodes in the list in the code, and if this contiguous set corresponds in the hardware distribution to the one that are on the same node, which would make sense, but this depends on how the hardware is set up, but I think is the default usually, then it will be in this way. Yeah. Okay. Vabbè, this is simple. Yeah, so this band parallelization again is the same thing that I said. So you could actually divide the number of processors in the same in a subset. This is what I was talking about FFT. What is it? Something important to be said here? Yeah, so this is heavy and frequent. So, but if it is, if the communication is good, then it scales very well. May scale very well until the FFT 3D dimension is reached. There is this linear algebra parallelization that can be used, and is kind of independent from the previous everything that we said before. I mean, the group, there is a group, subgroup of processor that is used to diagonalize the small matrices, and if scala pack is a variable, then it should be efficient. If not, there are some other parallel algorithms that are used in place of scala pack, but I don't think they scale very well, right?
No, it doesn't work very well. The alpha, called alpha library, works much better than that, and better also than Scalaba.
Okay.
But in order to compile with alpha, you need something new.
Yeah, anyway, Volker Broom actually wants to... No, but he's willing to help. So let's keep in touch with him. Yeah. Okay.
I didn't manage it 2 days ago.
Yeah, no, but I mean, Volker is going to come in June or July. So, and he was willing to make it work, his alpha thing work with more code, in particular with Quantum Espresso. So we should keep in touch with him. Yes?
Is the alpha library convenient for any system? Because someone told me that it is convenient only when you have a very large system of having something like thousands of electrons, while if you have a small system, it would be more unstable compared to
unstable, I don't know.
System and it's irrelevant what you
Yeah, for a small system, you don't even need the Scala pack. I mean, I think you just diagonalize it on a single processor. But if you start having thousands of electrons, not atoms, thousands of electrons, I think it may be significant. And then I don't know alpha, if the alpha is stable or not. Well, if it is not stable, then we should tell Folke that we we won't use alpha unless it make it stable. Folke Bloom is a guy that is behind the alpha development. I mean, is the one that pushed for it. Okay. Okay. So and then there are, since there are many other small places in which some over atoms, some over bands, some over grid points of some specialized set of points are needed. Then there are some small, I mean, but these are all local stuff that don't really interfere with the rest, and you don't really even see from the command line. So what was the point? Okay, so what is it? OpenMP versus MPI. What are the dangers?
Well, it is no longer. I don't think it applies any longer, but once upon a time you had to be careful with some machines to avoid that the same MPI process.
So thread-safe stuff. There was a competition. The OpenMP used the code that were for MPI, so that you have basically the code doing two things at the same time.
So two threads on the same
MPI.
Same core or things like that. It used to happen. Now, typically the software now, parallel libraries typically don't do that any longer.
Okay, so let's say, so the main use is that you can extend scaling, scalability, and okay, let's hope these dangers are not anymore used. Okay, so this is a kind of summary of the different things. So image pool, bands, and RNG distribution. So this is what we mentioned, and then in addition to that, if you have many FFT at the same time, you can do task parallelization. If you have your small matrices are big, then you can use this linear algebra parallelization, and you can play with the OpenMP, try to inside the node to exploit that as well. But okay, so this is the main list, and basically you see these two more coarser levels, they involve very little communication, and so they do not distribute memory, of course, but if possible, they don't give much harm. I mean, if you can use them because your calculation has many k points, or you are doing many replicas for some reason of the same calculation, then this is something that you can for sure use. But the main one that you can always use basically is this G vector and R space distribution, which is high. So distribute most of the RAM, scale well until it reaches the limit of the number of planes that you can distribute. It's well balanced, and so this is basically the principal way things are distributed, and around this you can try to distribute groups of bands, either with the band parallelization or with a task group parallelization, which is limited to the FFT part, and yeah, that's it. So basically. So, okay, so different codes implement different strategies. So, I mean, the NAB and many PW and the phonon code implement this image parallelization, and all the others. PW implement basically most of them. The bands parallelization only for hybrid functionals, while Carparinello implements also the band parallelization, and the phonon code implement, the image and all the others, not the bands, and some other code, I don't know, depends. But most, I mean, the ones that are usually implemented are the RNG parallelization and the K-point parallelization. Okay, so. So when you have a system, how many processors should I take? Depends. Okay. Right. So what you need to do basically is see how many processors you need to fit. I mean, such that the RAM that you have available is such that your system can fit in the. I think this is the main thing. So you need to. The real bottleneck is that you must be able to put your system on a certain number of processors, and then the system can run. And so this will define the minimum set of processor that you need to use, and then you can use K-point, etc., to extend the scalability. But this is the minimum that you must use, and in a certain sense, I think that the minimum is the best. Maybe with the condition that you use full nodes. I mean, if you have a node with 16 processors, it doesn't make sense to use 12 if your calculation would fit in 12, but I mean, you have 16, the communication is probably good inside, so you just take 16. But let's say this define what is the minimum set that you want to use, and then maybe if you want to extend the scalability because you want to do faster calculation, etc., then you can decide, okay, this 16, but I have many K-points, so then I use more nodes with more pools, and you're always trying to use the smallest or the smallest reasonable number of processors for the inner distribution of plane waves and real space data. Yeah.
By the way, on many systems, you pay an entire node even if you don't.
Yeah, exactly. So this is the point. Yeah, also. So it's pointless to use. It's pointless to use half of the node. I mean, if you pay for one, so then. And also the communication inside the node should be fast, and so things should scale good, well. Okay. And so what is suggested here is that, okay, you do some tests and see, benchmark your job and see how much you pay, how much it takes. So what should you look to understand if your calculation is, let's say, doing well, I mean, it's using well the data. Okay, one thing to check is that what is the distribution of the processor that you are using, and so in the header of the output, then it should write exactly what you are using, so how many processors in total, how many for the RNG distribution, how many pools, if you are using images and all these things. So this is kind of summary of what is your distribution of your data. And then one thing to check is that there is later on a section in which it say what are the distribution of the data. and you should check that these columns that I was mentioning when I was describing how the data are distributed in reciprocal space, each processor should have a reasonable number of sticks. I mean, because you want balancing, you want a load balance between these processors, and basically each processor should have similar number of sticks, similar number of plane waves, similar number of plane waves for a wave function and for the density. So these things are all listed in the, I mean not listed, but given some average and some standard deviation or some minimum and maximum value across the processors in the G vector stick info section. Okay, and so basically if these numbers, the number of sticks is too small, this means that in the end the processor doesn't have much to do. I mean, doesn't have many plane waves to work on, and then eventually everything is going to be dominated by the communication. So this means that probably you could use a smaller number of processor, or let's say a different distribution of the processor in a different, with more pool or something like that, to make this number being at least a few tens of G vectors. Okay, so a few sticks, which means at least a few tens of G vectors per processor. And so this is just a summary of what the code does and how the data are distributed. If you go to the end of the calculation, then there is a time report, and you will see that most of the time is spent in diagonalizing the Hamiltonian. And in the diagonalization of the Hamiltonian, most of the time is spent in applying the Hamiltonian to the vectors, and in the applying the Hamiltonian to the vectors, most of the time is spent in doing FFT. So in the end, then there are some timing, and there is some time for this FFT scatter, which is the time spent inside the fast Fourier transform routines. That there are, okay, 3 of them different, because it depends if you transform wave function, density, or potential on the smooth grid. Anyway, they are all together, and so how much time is spent in the FFT scatter with respect to how much time is spent in the rest of the FFT tells you if you are communicating too much. So if your bottleneck comes from the communication or from the calculation. Again, this tells you if you are trying to push too much the parallelization, to extend too much the parallelization. Okay, what is this? Yeah, if in the end the code print both the CPU time and the wall time.
Except that for a few strange machines for which they are both the same.
Okay, but
The previous Cineca machine.
okay, vabbè. Okay, so but in normal machines, we can ask tomorrow Carlo Cavazzoni about the previous Cineca machine. Okay, Fermi, yeah, okay. Well, we don't know about Marconi because we can't really use Marconi yet, but okay. If wall time is so much larger than CPU time, means that there is some bottleneck, something that is actually waiting. I mean, that is hanging somewhere, and so there is maybe you are trying to what is it? You are trying to use too many threads, or there's some
if you have threads, if you have OpenMP, the CPU time is the sum
okay. Over threads.
Overall threads. So you may have a CPU time exceeding wall time.
Okay, but so this doesn't.
The opposite of what happens when there is something wrong.
Yeah, but this doesn't mean that it's good. I mean, you don't really know. I mean, you need to divide the CPU time by the number of threads, okay, to make have an estimate. Yeah. And the other thing, another thing that is printed is how much time is spent in the diagonalization of the small matrices. And so if this, you will see that you have many processors, everything goes down and doesn't cost any more because everything is parallelized, but this is actually became the bottleneck. This means that, yeah, you're spending most of the time now in doing this standard diagonalization, and then this is where the linear algebra parallelization may help, or okay, you can try to use it even before, but in general. But let's say one thing to see is what happens to this standard diagonalization of nominally small matrices that may be in the end significant if you don't distribute the diagonalization. Okay, there is in the PW user guide, there is some more detailed explanation of what actually one can look to understand what different numbers that the code print mean, and how this can help in setting the parallelization strategy better. Okay. Well, I don't know. That's it. Okay, these are. I think it's done. Yeah, I'm done. So I mean, yeah. Oh, sorry. I thought I was. Okay, yeah. So that's it. So this is just example of scalability, but okay. I stop here. Sorry. Any more questions or things? So going back. Here, I think this is just a good summary of the what are the different options, and maybe later we try to see. I mean, you have some example, and we will see. Okay, I will stop here.